Hello, my name is Jonathan David, and this is my presentation on supervised machine learning using neural networks for reward-based games. So the purpose of this project is to show that neural networks can be applied to a wide range of interesting areas. If we can create an artificial neural network that is capable that uses back propagation to do pattern recognition and teaches to play tic-tac-toe, it serves as a proof of concept that we can use neural networks for other more complicated tasks. And this paper also serves as an introduction to neural networks for those who have no background in it. So why do I want to use a neural network? So it is able to adapt itself to data without any prior assumption of the functions. So you don't need to teach it what the functions are. You only need to tell it if it's right or wrong. And it can kind of adjust itself based on that. And if you give it an error, it can adjust the weights in its own system according to the errors. That's going to be described later. And it acts as a universal function approximator. So it can kind of model a wide variety of functions. And if it can model a wide variety of functions, it can be used in many different areas. So it's not going to model these with perfect accuracy. It's going to be a little bit wonky. So the system needs to be trained with training sets before it's used in any sort of application. So let's start with the basics. You have the neuron body, which is the basic element of the neural network. It accumulates all inputs from the system, and each input is given a certain weight by the neural link. And the neural body only outputs one signal, so it outputs one signal to the entirety of the next layer. So it doesn't output a signal tuned to each neuron after it. They all receive the same signal from that one neuron. The neural link applies a weight to a signal received by a neuron. So if it deems that a link is important, it's going to have a much higher weight than a link that's deemed not important. A not important link will have a weight close to 0. And the neural links, of course, connect all the bodies together. And together, the neuron body and the neural link will create a neural network, which is greater than the sum of its parts. You can teach it to do very complicated tasks. So the variable function allows for a neural network to adapt to its environment. That is the weight of the links and the bias of the neuron. So neurons can apply a bias to its output, kind of just shift the level up a little bit. And the weight of the links can be changed to kind of optimize an algorithm. So supervised machine learning was used in this study. That is, it requires a training set. And you have to tell the machine how it's doing. You have to give it an error function so that it knows how to adjust its own values of weights and biases in the neurons. So calculating the error is an extremely important task for supervised machine learning. So the project goals I want to accomplish are to create a neural network model, train an untrained system to play tic-tac-toe, and measure the effect of changing the number of neurons and the learning rate of the system. So if we change the number of neurons, we expect to see that a small number of neurons will have a harder time learning the task, and a large number of neurons will have a better rate of learning. And if you change the learning rate, it should change how fast the system learns how to accomplish its goal. So we begin with backpropagation of the neural network. This is a supervised method. The feed-forward neural network has a simple learning algorithm, but unfortunately the links are static and it's unable to change to the environment. By introducing backpropagation, which is the errors fed back to each neuron and link, the neurons can adjust their biases according to the error, and the links can adjust their weights according to the area. So if this is done, then pattern recognition is achieved. The system can change its weights and biases and links such that it will approximate the function that's being fed into it. So forward propagation of the neural body begins with this. It accumulates all the inputs. It adjusts the input with the bias. The bias is fed into an activation function, and this is output to a link. It's shown in this figure here. So you see that the top end kind of is the forward propagation, and the bottom end is the back propagation. So the back propagation receives an error from a link. It multiplies this error by a derivative of the activation function. I know it's kind of difficult to see here, but I'll explain that later. It accumulates this error, and it passes the error to the prior link. So doing this back propagation allows the machine to activate self-learning. So the logistic sigmoid function is shown on the right. This is the function that we use to activate the signal. It's a continuous differentiable signal, doesn't exceed the bounds of 0 or 1, and it kind of acts as a filter for the output. So we're not just outputting a straight 0 or 1, we're kind of outputting a continuous value that we can use later to employ gradient descent. And this is important for our purposes because it is how we will teach the machine how to adjust its weights. So forward propagation of the neuron link is done in this manner. It receives an input from a neuron, it multiplies the input by a weight, and it passes the weighted output to the next neuron. And backpropagation of a neuron link is that it receives an error from a neuron, multiplies this by a weight, and we get a weighted error that will then pass into the neuron before it. So, if you have several layers of neurons, this is going to kind of magnify the error all the way back to the input. And the links will change their weight at each propagation step. So what is gradient descent? First, we take the error function at the output. So we kind of take the difference between what we got and what we were expecting. We calculate the derivative of the error function, and the output value, of course, is determined by the activation function. So we also need to take the derivative of the activation function if we want to take the derivative of the error function. That's kind of only natural. We can't take the derivative of the error function alone. We kind of need to know what caused the output. So in order to derive the error function, we also need to derive what caused the output. So we use the derivative of the error function to adjust weights accordingly. This is shown in the top equation. It's delta omega I is equal to negative gamma, the partial derivative of the error with respect to the weight, So by doing this, on the equation at the very top, we're able to change the weights based on the error. That is, the higher the error is, the more we change the weight. And this kind of is a gradient descent, kind of points towards the local minima in an area. So we want we kind of want the gradient to equal 0. If we know the gradient is equal to 0, then we know that we've kind of reached a local minima, and then we can kind of just relax there, and that we've optimized the function at least to some degree. You can kind of think of it as throwing a marble into a bowl and letting it roll around until it sets to the bottom. It's kind of an intuitive sense of what we're doing. Unfortunately, there's a chance that the algorithm gets stuck at a local minimum. So a local minimum is not the absolute minimum, the difference being that you can imagine if you're on a cliff and you're standing in the little divot, that would be a local minimum to the top of the cliff. But if you're looking past the horizon, you can clearly see that there's a drop in front of you. But if an algorithm can only see so far, it won't be able to see the massive dip. So the chance of getting stuck at a local minimum means that you've optimized the function to a degree, but there's a chance that you haven't found the absolute minimum. So here's an example of gradient descent that I'm just kind of showing you. You can see that it kind of zigzags towards the local minimum of a function, both on the left and the right. And the zigzag pattern just makes sure that it kind of happens when it's close to the minimum, but can't exactly hit it. So the neural networks we have under test have 9 input neurons and 9 output neurons and 2 hidden layers. The first layer can be modified between as many neurons as you would like. In my tests, I've used 24, 48, and 96. And there are 9 outputs in the second layer that can't be adjusted. That's going to determine the output. Only one of these neurons can be set to 1 because it's kind of saying which box of tic-tac-toe you want to check. And the learning rates are adjusted between 0.3, 1.0, and 2.0. So the results are kind of a success. You can see that at n equals 48 neurons, we have it kind of settles towards about 0.2 error. At n equals 48, it kind of settles at 0.15 error for the learning rate of 0.3 and trends towards 0 for a learning rate of 1 and 2. And with 96 neurons, it settles at about 0.25 error for a learning rate of 1 and 0.3, and it trends towards 0 with a learning rate of 0.2. So thus we know that the system is capable of pattern recognition, and neural networks are capable of learning to play tic-tac-toe. They can be applied to more complicated tasks. It doesn't have to be a simple game. This is only a proof of concept. However, the system is not without its faults. We can see that with too few neurons, it results in kind of a higher average error. With too many results in poor optimization. So if you have too many neurons, it can't optimize itself as well. It has to, there are too many weights being adjusted. It kind of complicates the function. And that learning rates must be carefully selected. A high learning rate is very unstable. You can see this in the far right figure, where at about 56 you see a sudden dip. That is caused by the function escaping a local minimum and going towards a lower one. But it's also possible for this system to find a higher local minimum. So we kind of don't want that scenario to happen. And worse yet, the system can get stuck at a local minima, as I've been describing already. The first 2 images show it getting stuck. The blue line is much higher than the other lines, and it does not find the way down. And the figure on the far right it managed to escape 2 local minimas, but this is done by having a very high learning rate. And like I just mentioned before, a high learning rate makes the system kind of unstable, so we don't want to depend upon that. So the conclusions are that the artificial neural network with backpropagation are capable of pattern recognition and thus can learn to play tic-tac-toe. To improve neural networks, a better algorithm for error minimization can be used. We don't need to use gradient descent. It's only one way to minimize the error. If we can find a better way of doing this, then it may be possible to find the absolute minima every time. Since the system can be taught to play a simple game, it can also be taught to perform more complex tasks. And it is best to test the system with several different neural networks such that we don't get stuck at a local minima. And if we have more training cases, we can see approximately what to expect in a well-trained system. Here's a list of references. These are used to kind of find the images and learn about neural networks. And now I'm going to show an example of the code running. So here's Visual Studio, and this is the code provided by one of the links that I have in the references. You can see here that we can set the number of neurons in the first layer, and by going to the neuron body class, we can set the rate of learning, and we can set the weight. So this is kind of like what the algorithm runs off of. And if we hit start, we can see that it's going to take a second. You can see that at 10 iterations, it has an error of approximately 0.4245. And at 10 iterations, we see that the error that drops down to about 0.350. And the next iteration, it drops again to 0.303. And we expect the next step to also be lower. And this will continue for as long as you would like. You can set the iterations to be as high as you want, and you would expect to see the error continually go down. However, it'll eventually hit a plateau. All right, I'm going to cancel this. And that's it. That was my presentation on neural networks. I hope you've learned at least one new thing. Have a great day.